It is the third degree polynomial, which does mean that we should have 3 solutions, okay? Because it's x cubed, so it should hit the x-axis 3 times is what we're looking for here, okay? So I'm going to plot the point -2, -2. And I can see right now that I didn't draw enough spaces. That's okay. -1, 2. We have 0, 0. We have 1, -2. And then I have 2, 2. So what happened is I get a function that looks similar to this. And you'll notice it does hit the x-axis 3 times. We didn't find exactly where it hits the x-axis, those solutions, but it does hit 3 times. Okay, and our goal here is for you to tell me when is it increasing and then when is it decreasing. Okay, so start on the left-hand side. You're the little red bug. Okay, what are you doing? As you're coming from x is infinity, what am I doing there? I'm increasing, okay? So I know I'm increasing from -infinity. Notice I use a parentheses, okay? Because infinity never has a bracket. And I increase until I get where? Now, guys, you're looking for the x value. Right here, right? At this point, right here at the top, I'm at the top of the peak. What is x right there? -1. So I'm increasing from -infinity to -1. Guys, you don't put a bracket on that -1. Yes, the function actually equals -1, 2. But at that point, and you'll learn this in calculus, you're not actually increasing. He's stagnant. He's sitting there. He's at the top of the curve. He's at the peak. He's not doing anything. He's sitting. So we don't put a bracket on him. It's parentheses, okay? So he's increasing from -infinity to -1. And then what's he going to start doing after that? He's going to start decreasing. So he's going down. He starts going down around -1, right? So I put a parentheses on there from -1. Then we'll turn in purple since he's decreasing. He's going down, 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 down until he gets where? 1. Good. So he decreases from -1 to 1. And then what? He's back to increasing from 1 to a positive infinity. Correct? Yeah. Because as x gets bigger and bigger and bigger, what happens? That graph goes higher and higher up is what happens. Okay? So that's your answer. You were looking for it increases from -infinity to -1, from -infinity to -1, and 1 to infinity. Yes, ma'am. This point right here is, -1, 2. And then this point right here at the change is 1, -2. Okay, and so that -1, this -1, comes from this right here. He increases until he gets to -1 on the x value. Then he starts decreasing somewhere right after -1. He decreases until he gets to a +1. And then somewhere right after +1, close to +1, he starts going up again. Okay, he starts increasing again. Okay, that is example 1. Let's talk about a relative max and a relative min. So we're going to take this same function that we had, and this is a function, okay? And yeah, I'm squeezing it in over here. I'll write some things. We're going to make it fit. Okay, I'm redrawing my same picture here, my same function. I still have points at -2, -2, right? Yeah. Then I had one at -1, 2, 0, 0, 1, -2, and then 2, positive 2. Okay, and you'll notice we talked about this point right here, the negative 1, 2, because he got up there and he started going down the hill, and then he got over here to 1, negative 2, and he started going back up. This negative 1, 2 right here is known as a relative maximum, and this is a relative minimum. Okay, sometimes the word local max is used, or local min is used instead of relative. If you take more math courses and different textbooks, sometimes you'll hear it called a local max or a local min. You may have even heard it called that depending on your Algebra 2 class. You may not have called it relative. It's relative because we're saying it's relative to the situation, to its environment, because technically I could find higher points on that function. But in that particular area, that spot on the graph, it is a relative or local. It's localized right there, okay? Now, how we discuss those is a little tricky, okay? We would say this graph has a relative maximum at negative 1, okay? So the at part is the x part, where it occurs, okay? So that relative max is at x equals negative 1, but what is the maximum? The maximum is 2, right? The x part tells you where it's at. The y part tells you what it actually is. And the only reason I go over that is because your homework does that. Your homework will go, where is the relative max? And then it'll go, what is the relative max? Okay, where it's at, and I used to do it like Mount Everest. Highest point, like I don't know that really Mount Everest is the highest point on Earth anymore. Is it? Okay, and I would go, where is the highest point on Earth? That's in Nepal, right? Isn't it in Mount Everest in Nepal? Yeah, yes.
Part of the Himalayas.
Yes, and then what is the highest point on Earth is Mount Everest. Two different answers. It's the same. That's an absolute max. Yes, I'm one of those people that it won't ever happen. I can't climb well, but I think it'd be pretty cool. Yeah, I might, it's a tourist attraction now. It's like if you can pay, those poor Sherpas are the ones that really should make all the money because, they set up all the ladders, they scale all that stuff all the time. But it's the companies that hire them that make all the money. The Sherpas don't make that much money. Anyway, we would say this graph has a relative maximum at negative 1 and the maximum is 2. So the x value is the location, and the y value is the max/min point. And I put max/min because it works the same for minimum. It goes, where is the relative minimum? What is the relative minimum? Okay? All right, we good with that? Let's talk about tests for symmetry. Okay, so if I have a function that looks like this, I've got a point at 2, 1, and I have a point at negative 2, 1. And it looks like this. Okay? This point right here, we said was 2, 1. This point is negative 2, 1. Okay, and yes, I know it's not, they don't look exactly the same on both sides because that's how I drew them. This graph is said to be symmetric about the y-axis. And if you'll notice, 2, 1, which is xy, right? That's an xy. What do we also have? We have a negative 2, 1, so that means a negative xy is present. So the test for symmetry about the y-axis, to test for it, we change the sign of x. And we're going to practice this. After we do a few other ones, okay? So that's about the y-axis. If I'm looking about the x-axis, let's see what it looks like. Now, you'll notice that this graph about the x-axis, I still have the point 2, 1, but this time I'm going to have the point 2, negative 1. Okay? So I have the point 2, 1. I have the point 2, negative 1. And I was saying this graph is not a function, correct? Fails the vertical line test here. This is symmetric about the x-axis. And guys, what that means, if we're saying symmetric about an axis, that means if you took that graph and you folded it over, in this case, the x-axis, it would match up on itself. That's how I know it's symmetric about the x-axis. But you won't always have the graph, and you don't always have the ability to see that, okay? You don't automatically see that in your head, pretty much. So you have to be able to take the equation and go, okay, well, is it going to be symmetric about the x-axis, or is it going to be symmetric about the y, or is it going to be, in a minute, symmetric about the origin? Okay, so that's why we listed things like, okay, this is xy, and here I have x negative y, right? So when we test about the x-axis, to test for symmetry about the x-axis, we want to change the sign of y. Okay? Does anybody remember what we do for the origin? X and y. Origin is pretty much a double flip. You flip it over the y, you flip it over the x, and there's symmetric about the origin. Okay? So, when we have symmetric about the origin, we still got our point 2, 1. Okay? And then we're going to have our point negative 2, negative 1. Okay, this is symmetric. This is negative 2, negative 1, negative x, negative y. It is, whoops, sorry guys. Symmetric about the origin. Okay, And to test for symmetry about the origin, change the sign of x and y. Okay? And we'll do some examples. Okay, example 2. Does anybody remember about even and odd? We talk about even and odd in here, but I can go ahead and write it on here. If a function is even, it is symmetric about the y-axis, okay? Even function. And like I said, I'll talk about it in a minute, but we'll go ahead and write it on there. And then if a function is symmetric about the origin, it's an odd function. Notice we don't have one for symmetric about the x, but like I said, this isn't a function. When a graph is symmetric about the x-axis, it's not a function. It's still a graph, but it's not a function, and these are specific to being functions, even and odd are, okay? Okay, so example 2 says determine whether the graph of y equals x squared minus 1 is symmetric with respect to the y-axis, x-axis, or the origin. Okay? So you actually have to test for all of them. Okay? So you start off, it says y-axis, so we're going to test the y-axis. You write down the original function to start with. Okay, the original equation. Y equals x squared minus 1. Can some of you see what that is? You remember what that looks like? It's quadratic. Yeah, parabola. Vertex is at -1. But you don't have to. Okay, so if it's y-axis, I change the sign of who? X. So I go through there and I go, okay, well, y equals negative x squared minus 1. So you change all the positive x's to a negative x. Okay? All right. So then you work it out. This gives me y equals, well, what's negative x squared? X squared minus 1. Did I get the same as the original? Yes. Okay? These are the same. So, yes, it's symmetric about the y-axis. Okay? You can have some functions, you can have some graphs, not functions, that are symmetric about more than one thing. Okay? Such as if I took a circle centered at 0, 0. Okay? So you have to, my point is, you have to go ahead and test for symmetry about the x-axis, and you have to test for symmetry about the origin. Okay? Just to make sure. X-axis. Okay, so I've got y equals x squared minus 1. This time I change the sign of the y because I'm testing about the x-axis. So I have negative y equals x squared minus 1. Well, guys, that's really just negative y equals x squared minus 1. I need to get y by itself again because that's how it originally started out, right? So if I'm dividing everybody by negative 1, that winds up giving me y equals negative x squared plus 1. Is that the same as what I started with? No. So not the same. So that's a no. Okay? And then finally, if I look at the origin, I start with my original again, y equals x squared minus 1. Origin says change both. So this gives me negative y equals negative x squared minus 1. Well, that gives me negative y equals, you've already told me negative x squared is positive x squared minus 1. Divide everybody by negative 1. That'll give me y equals negative x squared plus 1. Is it the same? No. Nope, not the same. So that's a no. So you do find that it only is symmetric about the y-axis, correct? Yeah. Okay. Oh, all right. I need to flip. We're going to do another one. Okay. Example 3. Once again, we are going to determine whether the graph of y to the 5th equals x cubed is symmetric with respect to the y-axis, x-axis, or the origin. This one's not as easy for you to, even if you see the graph that comes from the equation in your head, this one's not as easy for you to see because it's in terms of y to the 5th, and you know you'd have to take the 5th root of everything. So it's easier just to test here. So let's do y-axis. We start with our original, y to the 5th equals x cubed. Okay? If I'm checking about the y-axis, I change the sign of x. So this is y to the 5th equals negative x cubed. Well, that's still y to the 5th equals, okay, what's negative x cubed? Negative times a negative gives me a negative, and then x cubed. Is this the same? Nope. That's a nope. So that's a no. Okay, x-axis. Once again, I've got y to the 5th equals x cubed. This time when I'm checking about the x-axis, okay, I change the sign of y. So I've got negative y to the 5th power equals x cubed. Guys, a negative 1 to the 5th power, since it's odd, is going to be a negative 1, right? When you take something to an even power, when you take a negative number to any even power, it comes back positive because it's got that square in there. If it's an odd power, it's going to come back negative. Negative 1 times negative 1 times negative 1, well, that was negative 1, times negative 1 is positive 1, times another negative 1 is negative 1. If it's to a 5th power, it's coming, and it's an odd number to it, not odd, it's a negative number to an odd power, it comes back negative, okay? So this gives me negative y to the 5th equals x cubed. Our equation started out as a positive y to the 5th, so I'm going to divide everybody by negative 1. And that gives me positive y to the 5th equals a negative x cubed. Are they the same? Nope. And that's a no. And finally, the origin. Now I need to change the sign of both. So I start off with my y to the 5th equals x cubed. I say negative y to the 5th power equals negative x to the 3rd power. Okay, negative y to the fifth gives me negative y to the fifth. You've already told me that. Negative x to the third power is negative x cubed. I'm going to divide both sides by negative 1 because I want a positive y to the fifth like I started with. That'll give me y to the fifth equals x cubed. Are those the same? Yes. So, yes, it is symmetric about the origin. Okay. The next little part, we touched on it a little bit already. An even function, if a function is even, notice it has the word function in it. Okay, even function is a function whose graph is symmetric with respect to the y-axis. Okay. Odd function is a function whose graph is symmetric with respect to the origin. Okay. So example 4, we're going to determine if the function is even, odd, or neither. Okay, so example 4, determine whether each graph is the graph of an even function, an odd function, bless you, or a function that is neither. Those are some long directions. Okay. So A, they're actually giving me a graph here. Move my A out of the way. Okay, so you think this is even, odd, or neither? What does it appear to be? Please note it is not drawn correctly because I drew it.
It appears to be even.
It appears to be even. Good answer. Yes, it appears to be even. Okay, so it's even. Y-axis, even. Okay, B. What if I just have this little chunk right here? Even, odd, neither. Neither, because there's no more to him, is there? Like if I fold him over the y-axis, nothing happens. Like there's nothing for him to match to, right? So that's neither. Okay. Then C is going to look something similar to not that. Let me go from the other way. Okay, this one is supposed to be, okay, this one's supposed to be odd because it's supposed to be the origin. And guys, the way you do that is flip him over the y-axis. So if I flipped him over the y-axis, then he would go like this, right? To start with, this little chunk right here. If I took the first quadrant and I flipped him over the y-axis, he would go like this, right? Okay, now flip him over the x-axis. Does he come down here like this? Does he match on himself? Yes, he does. Okay, so an origin is a double flip. So since it's origin, it appears to be the origin, it is odd. Now, their pictures will look much better. Okay, just so you know. Okay? Example 5. Of course, then they're going to give you some where we actually have to test the function. Determine if, and I'm going to shorten these directions, even, odd, or neither. Determine if even, odd, or neither, and then tell who it is symmetric about. So this means that we're going to kind of have to test for that x-axis also, because if we need to test whether it's symmetric about x, y. Actually, it just says y or the origin. They're only worried about even or odd. So we only have to deal with, you don't have to deal with x here, okay? A is f of x equals x squared plus 6. Now, this may bother some of you guys because what does that say? That says f of x. What have we been using? Been using y, right? Up here where I tested, it was y to the 5th equals x cubed. It was, over here it was y equals x squared. But now I have f of x equals x squared plus 6. Well, what did we say f of x really was? He's just y. So if you need to rewrite him as y equals x squared plus 6, you can. No big deal. If I'm testing, let's start off with, we want to do even first. If I'm doing even deals with the y-axis, correct? Okay, which means I need to change the sign of x. We good? So that means I've got y equals negative x squared plus 6. And those of you that noticed it was a parabola, you know it's going to be symmetric about the y-axis, which gives me y equals positive x squared plus 6. And is that the same? Yep, it's the same. So he is even. We do know that. And he is symmetric about the y-axis. Okay, we'll try odd also. Okay, so if I'm trying odd over here, that means origin. So that means I change the sign of who? And the x. Good. Both of them. So I've got negative y equals negative x squared plus 6. That gives me negative y equals positive x squared plus 6. When I divide by that negative 1, that's going to leave me with positive y equals negative x squared minus 6. Was that the same? No. I started off with y equals x squared plus 6, so that's a no. This was f of x equals x squared plus 6. So it is not odd, it is not an odd function, and it is not symmetric about the origin. You got your even and your y-axis, okay? That was part A. Let's look at a B, at least. We don't have to do, we'll do one more, we'll do B. I can't fit him in there. Same directions, of course, and I have g of x equals 7x cubed minus x. Okay, so let's start off with even, which means that we're talking about the y-axis. This is really y equals 7x cubed minus x. If I'm checking about the y-axis, I need to change the sign of x. So y equals 7 times negative x cubed minus negative x. Be careful, okay? That's going to give me y equals, well, negative x cubed is negative x cubed. So that gives me a negative 7x cubed plus x. Was it the same? No. So that's a no. So I know it's not even and it's not symmetric about the y-axis. Okay, so now I'm going to try odd. Odd means origin. Okay. So I'm going to start off with my y equals 7x cubed minus x again. I'm going to change the sign of x and y here. So I've got negative y equals 7 times negative x cubed minus negative x. Negative y equals negative 7x cubed plus x. Okay, I need to get it back to just y equals, because that's how I started. Divide everybody by negative 1, and that's going to give me y equals 7x cubed minus x. Is that the same? Yes, it is the same. That means it's odd, and it is symmetric about the origin. Okay. Let's talk about a piecewise function. Y'all will remember piecewise functions when I show them to you. Because they look hard, but they're not really difficult. Okay. And we're just going to do it. A piecewise function, those are graphs that they look kind of rigid. They'll have differing straight lines, nothing smooth, and they're defined for, well, there will be sometimes smooth parts, but they're defined for certain domains, okay? So, and the easiest way to do them is just to do them. If I have the function c of g, and it equals, it'll say 40, and then it'll say something like 40 plus 0.6 times g minus 15. It equals 40 if 0 is less than or equal to g is less than or equal to 15. And it equals 40 plus 0.6 times g minus 15 if g is greater than 15. Okay? So the information on the right-hand side, tells you, okay, when the value is a certain number, do this. Do on the left. So if g is 5, I know that c of g is just 40, right? Any value between 0 and 15, any x, any g between 0 and 15, you will get the answer 40. The answer is 40. If you're over 15, if you get a value over 15, like 20, then you put it in the bottom one. Okay? So let's look. I want, this is example 6. I think, is it example 6? Mm-hmm. Okay. A says we want C of 5. Well, I go over here and I go, okay, well, C of 5, does it fall in this first one in the top, or does it fall in the bottom category? Falls in the top category. Good. Well, what does it say? If it's falling in the top, what does C of 5 equal then? 40. Well, that's pretty easy, wasn't it? You're like, it can't be that easy. It is. Okay. It's a little harder on B, because on B, we have C of 50. Okay, does it fall on the top or the bottom? Bottom, because this says if G is greater than 15, G is 50. So I need to use this formula right here. So C of 50 is going to equal 40 plus 0.6 times 50 minus 15. All I did was plug in 50 for my G, right? Okay, so 40 plus 0.6 times 50 minus 15 is what, 35? And you do get to use your handy dandy tiny calculator. Somebody tell me, well, that's what, 30 carry a 3, that's 18, that's 21. Is it 21? Is 0.6 times 35 21?
Yes.
Okay, so that's going to give me 61. Okay, not bad, right? That's all of that. Then sometimes you have to graph them. They'll tell you to graph them. Y'all don't really, sometimes you don't like graphing them. They don't give you anything too bad when you have to graph. It says graph the piecewise function. Defined by f of x equals 3, or x minus 2. It's going to be 3 if x is less than or equal to negative 1. And it's going to be x minus 2 if x is greater than negative 1. Okay, so we want to graph that. All right, we can do that. Here we go. So I'm going to take care of the top one first. It says when x is less than or equal to negative 1. Okay, well, here's x is less than negative 1 over here. So here's x is negative 1, right? It says y is going to be what? 3. Okay, so at negative 1, it's 3. What is it at negative 2?
3.
Yep. What is it at 3? Negative 3, sorry. 3. See where we're getting those from, guys? If we pick a number that's less than negative 1, what's the answer? 3. Y is 3. Okay, so that's all I've done is apply some of those points. You just like that. Now over here it says if x is greater than negative 1, since there's not an equal to, when I start at negative 1, I'm going to put an open circle there. Okay, so greater than negative 1, I'm going to plot some points over here, make my T-chart. So negative 1, 0, 1, 2, right? I got to know where to start. So I got to put negative 1 in there. Well, that's what, negative 3? If I put 0 in to the bottom, I get what, negative 2? If I put 1 in, I get negative 1. If I put 2 in, I get 0. So I'm going to plot those now. Like I said, be careful. This says x is greater than negative 1. So when x is negative 1, in that function, I would get negative 3. But I'm going to use an open circle because it's not equal to. 0 is negative 2. 1 is negative 1. And 2 is 0. That's enough. It's a linear.
So you leave one of those open?
Yes, and it's because it's the negative 1. Because negative 1 is actually equal to 3, but you've got to show where we start, And since he's not equal to there, we put an open circle. The rest of them are good. They're actually equal to there. Okay? And you've done it. You graphed your piecewise function. There is a piecewise function called a step function. I'm gonna need to flip that. Step functions. They are piecewise. Whose graphs form discontinuous steps. Okay? The greatest integer function is one of the most notorious ones. Okay? They are symbolized, and I'll show you a picture in a second, show you a graph, symbolized by, they'll say int of x, or you will see these double bracketed. A lot of your calculus books will use the double brackets like that, x, where int of x equals the greatest integer that is less than or equal to x. Some places will call them floor and ceiling functions later on. But for this textbook and this class, we just briefly discuss greatest integer function. So if I asked you what the greatest integer of 1 was, you would tell me just 1. What's going to be the greatest integer of 1.3? 1. Because it is the greatest integer that is less than or equal to whatever's in those parentheses. So it's got to be an integer. So it's got to be something like -5, -4, +5, 6, 7, 8. Can't be a decimal, can't be a fraction. It's got to be an integer. And it can't be bigger than what's inside the parentheses. So when I go the greatest integer of 1.9, what are you going to tell me? 1. You're not going to tell me 2 because 2 is bigger than 1.9. You just need the biggest, but its name kind of makes it deceptive because you're going, well, the greatest integer is 2. Well, no, we want the greatest integer that's not bigger than what's in the parentheses. Okay? Okay, it looks like this. No. They look like steps. They literally look like steps, guys. Okay? So there'll be a closed circle at 0, 0, and then maybe an open circle, at 1, 0. Okay? Then at 1, it actually equals 1, and it stays 1 until I get to 2. And then I have an open circle at 2, and then I jump. At 2, I do actually equal 2. And I stay at 2 until I get to 3. And then what happens at 3? I jump up to 3. And then for 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, all of those, or 3, 1, 3, 2, 3, 3, all of those, I stay at 3 until I get to 4. And at 4, I jump, right? I keep going. That's why it's called a step function. Your greatest integer function. This is y equals the greatest integer of x right there. That's what that is. That's what that function is. Okay? Okay. Okay. Last thing we need to talk about really quick, there may not be any homework problems on there. 6 years ago, sometimes, some semesters, they would tell me I had to teach it. Some semesters, they would go, no, you don't have to teach it. So I'm going to teach it. I'm not sure if it's on your homework problems. It will benefit some of you. It is definition of the difference quotient of a function. If any of you took an advanced pre-cal class in high school, or you did take calculus in high school, this will be familiar. F of x plus h minus f of x all over h. We use the difference quotient when we begin to talk about limits, okay? In pre-cal, at the end of pre-cal, and the beginning of calculus. The very beginning of calculus is limits. And the definition, if you take, and derivatives. And if you take a derivative by definition, you're taking the limit as f of x plus h minus f of x all over h approaches, as h approaches 0, okay? But that's, you don't have to do anything that hard here. It's just, can you figure out how to substitute things in, is all this is. Okay, so, but this is the difference quotient. It does become important if you take other classes past this one later on. Some of you have heard of the difference quotient before. I will say, Yana's probably heard of the difference. She's seen this before. You've seen this before, right? Yes. Yes. And you've seen this before, probably. Yes. You may have used f of x plus delta x minus f of x all over delta x. You may have had a delta x in there. Or you'll have a funny little, it'll look like that. Okay. Depends. Okay, so for you guys' purposes though, all it does is it asks you things like if f of x equals negative 2x squared plus x plus 5, it asks you to find the following. And they'll be nice to you, and in A, they'll ask you to find f of x plus h. And then in B, they'll actually ask you to find f of x plus h minus f of x all over h, such that h does not equal 0. Okay. Now, guys, to find f of x plus h, what did they do? They just took out x, and everywhere they saw an x, what are they doing? Plugging in x plus h, right? Okay, so this is really going to become negative 2 times x plus h squared plus x plus h plus 5. Okay? All I did was take that x out and put in x plus h. That's all I did. You did something very similar when we were doing function notation and we had the 3a. We put in 3a instead of just 3. Okay, that was getting you ready for it. So this is negative 2. Remember, this is x plus h times x plus h plus x plus h plus 5. You got to FOIL that x plus h times x plus h. That's going to give me negative 2 times x squared plus xh plus xh plus h squared. Then plus x plus h plus 5. I just dropped the parentheses on the x plus h. I can, because there's just addition on either side. Right? This is negative 2 times x squared plus 2xh plus h squared plus x plus h plus 5. Okay? That's, if I distribute that negative 2, I've got negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. I know y'all are going, there's way too many letters going on right now. Okay, you can't put anything with the negative 2x squared. It stays the same. Negative 4xh is just negative 4xh. Then we've got the negative 2h squared. You can't have anything with the plus x, the plus h, plus 5. We're good. I just rewrote the thing. We couldn't combine anything, right, guys? Now, I'm not going to go through the b part, but you take that. This is, right here, the blue right here is really f of x plus h, right? That's what that is. So you take that, you plug it in for f of x plus h in b, then you subtract f of x and it's all over h. I'll write that in before I post the notes, okay? Because we have 2 minutes. You want me? I'll write it in. Y'all just finish writing that, and then I'll write it in. Like I said, you may not have a homework problem that deals with that. But I didn't want you to